Hello everyone. Today we start section 4.3, primes and the greatest common divisors. First, primes. A prime is an integer greater than 1 that is divisible by no positive integers other than 1 and itself. Or also we can define it as follows. An integer p greater than 1 is called the prime if the only positive factors of p are 1 and p. A positive integer that is greater than 1 and is not prime is called composite. Next theorem. This theorem is considered the fundamental theorem of arithmetic. Every integer greater than 1 can be written uniquely as a prime or as the product of two or more primes where the prime factors are written in order of non-decreasing size. For example, the prime factorization of 13 is 13, of 21 is 3 multiplied by 7. 3 and 7 are primes. 100 is 2 multiplied by 2 multiplied by 5 multiplied by 5, which is 2 square multiplied by 5 square. 101 equals 101, so it is prime. 512 equals 2 multiplied by itself 9 times, or 2 to the power 9. 999 equals 3 multiplied by 3 multiplied by 3 multiplied by 37, which is 3 cube multiplied by 37. Next, trial division. It's often important to show that a given integer is prime. For instance, in cryptography, large primes are used in some methods for making messages secret. One procedure for showing that an integer is prime is based on the following observation. Theorem. If n is a composite integer, then n has a prime divisor less than or equal to the square root of n. To prove this theorem, we know that if n is composite, then by definition, it has a factor a, with a less than n and greater than 1. By definition of a factor of a positive integer, we have n equals a multiplied by b, where b is a positive integer greater than 1. We will show that a is less than or equal to the square root of n, or b less than or equal to the square root of n. If a is greater than the square root of n and b greater than the square root of n, then ab is greater than the square root of n square, which is n, which is a contradiction. Consequently, a is less than or equal to the square root of n, or b is less than or equal to the square root of n. Because both a and b are divisors of n, we see that n has a positive divisor not exceeding the square root of n. This divisor is either prime or has a prime divisor less than itself. In either case, n has a prime divisor less than or equal to the square root of n. From the theorem, it follows that an integer is a prime if it's not divisible by any prime less than or equal to its square root. This leads to the brute force algorithm known as trial division. To use trial division, we divide n by all primes not exceeding the square root of n and conclude that n is a prime if it's not divisible by any of these primes. Example, show that 101 is a prime. The only primes less than the square root of 101 are 2, 3, 5, and 7. The next prime is 11, but 11 square is greater than 101. Because 101 is not divisible by 2 or 3 or 5 or 7, it follows that 101 is a prime. Next, procedure for finding the prime factorization of n. We start by dividing n by successive primes, starting with the smallest prime 2. If n has a prime factor, then by theorem, a prime factor p not exceeding the square root of n will be found. If no prime factor not exceeding the square root of n is found, then n is prime. If a prime factor p is found, we continue by factoring n over p. Note that n over p has no prime factors less than p. Again, if n over p has no prime factor greater than or equal to p and not exceeding its square root, then it is prime. Otherwise, if it has a prime factor q, we continue by factoring n over pq. This procedure is continued until the factorization has been reduced to a prime. For example, to find the prime factorization 750 here, we can divide it by 2, and the result is 375. 375 is not divisible by 2, but we can divide it by 3, since 3 plus 7 plus 5, 15. So we'll have 3 here. 1, 2, 5. 125 is not divisible by 3. The sum is 17, but we can divide it by 5. And the result is 25. 25 is divisible by 5, and the result is 5. So we have the prime factorization 750 equals 2 multiplied by 3 multiplied by 5 to the power 3. And the textbook example, find the prime factorization 7007. Here 7007. None of the primes 2, 3, and 5 divides 7007, but the prime 7 divides it. And here we have 1001. Next, we try to divide 1001 by primes starting with 7. 7 again divides 1001. And the result here is 143. 7 does not divide 143. The next prime is 11. 11 divides it. And we have here 13. 13 is a prime, so we are done. So 7007 equals 7 squared multiplied by 11 multiplied by 13. For today, that's all. Thank you.